Hi guys, this video is going to be covering in the DC circuits unit. We are on lesson 2. Lesson 2 covers resistance, resistivity, and Ohm's law. This is in the Survey textbook. This refers to 17.4. In the OpenStax, it is 20.2 to 20.3. Okay, let's talk a little bit about resistance and resistivity. Those two words sound very similar, and they are very similar. Resistance is measured in ohms. So that's another thing, is that the omega is used for the ohms. That is a capital omega. We've used lowercase omegas before. And ohms is volts over amps. But we'll get to that. But I just want to show you that the ohm is an omega. So resistance is R, measured in ohms. It is electrical friction that hinders the flow of current through an object, turning electrical energy into heat or mechanical energy. Resistance is the value assigned to a specific conductor that indicates the degree of resistance to the passage of a current. So you've learned that current is kind of like water flow. And if there's nothing in the way, that water is just going to flow on through like a fire hydrant. Okay, but then we don't want the fire hydrant in our house, right? We want to slow it down, and so we do things like we make our pipes smaller. Or in our showers, you may not know this, but in your showers, there are devices in your shower to give you less water pressure so that you don't get blown away by your shower. Same thing with electricity, electrical current. We can slow down the electrical current by changing the shape of things. And so that's what resistance is. Resistivity is a similar concept. It is with a rho. This is another Greek letter, a rho. It's measured in ohm meters. It is a characteristic property of a material which determines how easily electrons will flow through it. It is a property of the material that indicates the degree of resistance to the movement of charge. So this is a table on page 608 in the Survey textbook that would show you the different resistivities. Okay, let's talk about these two and what their difference is. Here I have that resistance changes with things like surface area. Okay, I was talking about the water flow and, the fire hydrant and things like that. Okay, well, same thing with current. You could have a huge line, a huge wire, and it would allow a lot of current to go through. But if you have a fine wire, a smaller wire, then not as much current is going to go through. And that is changing the resistance. So the resistance changes with things like surface area. Whereas resistivity, that is the property of a material. So each material has a certain resistivity assigned to it, a numerical value. From the OpenStax book, here is an example showing us resistance and resistivity. And so resistance is our capital R, and it depends on the shape and the length and all of that of this cable, of this wire, whereas the resistivity is just the wire itself. And so on that same page in the OpenStax book, they have a table, and the Survey book has a table as well. And so it shows you what is the resistivity of silver, of copper, of gold, of aluminum, etc. And so each of these is a numerical value assigned to a certain conductor that tells you what is its resistivity. And so you could take a copper wire and have a really big fat copper wire, or you could have a really skinny copper wire. They would have the same resistivity, but they would have a different resistance. The larger wire would allow more current through, so it would have less resistance. The smaller wire would be thin and have more resistance. So that's resistance and resistivity. Resistivity is a property of the material. Resistance depends on the things like surface area. Here is a formula, and I had that up on the screen a second ago with the OpenStax book, but this formula shows us the relationship between resistance and resistivity. We can see that capital R is the resistance, and the resistance depends on the resistivity. It also depends on the length of the wire, and it also depends on the cross-sectional area of the wire. So some of you might know this, that how far away you are from something might change how well the signal comes through, things like that. Okay, Also, the cross-sectional area of the wire, a really thin wire, is going to have more resistance. And so those are all related here, and all three of those things, resistivity, the length, and the cross-sectional area, all will affect the resistance. Okay, let's take an example of copper. So the resistivity of copper is a quantity, from the table. We have a known quantity that is the resistivity of copper. It's going to have a specific resistance depending on the shape. So a copper penny will have a specific resistance that would be different from the resistance of a copper wire. However, they have the same resistivity because they're both made from copper. Okay, so obviously, that a penny is going to have a shorter length and a greater surface area, whereas a wire is going to have a longer length and a smaller surface area. So that's going to that's going to change the resistance, the overall resistance of the setup. Okay, this first question here, I have to say I don't have a ton of space here, but we are going to use this formula and we're going to use this information in that formula. So the question is, what is the resistance? So we are solving for R. The rho is the resistivity, so that's going to be this value. And the unit for resistivity is ohm meters. Now we have the length over here. The length is 2 meters. And the diameter is 0.5 millimeters. Well, a couple things we need to do with that. We need it in meters, and we need to remember what is the area of a circle, because I'm assuming that this wire is a circle, and the area of a circle is pi r squared. You might want to just remember that area is pi r squared. I believe that is given to you on the AP sheet. Yeah, I looked it up on the AP sheet. There's a section that has a bunch of geometry formulas, and that is a formula that's given to you on the AP sheet. Okay, but we need to figure out what that area is if the diameter is 0.5 millimeters. Well, if this is the diameter, first of all, the radius is 0.25 millimeters, and we have to convert it to meters, so we need to move it over 4 decimal places in addition to that. So let's just go ahead and write that out. And so the area of our circle is pi times r squared. And so we're going to put that into our calculator. Take a second with your calculator, put that into your calculator and see what you get. Okay, so you should have gotten 0.17 ohms. Let's just take a second to look at the units. I always think it's important to look at what's going on there. We have an ohm, we have a meter, we have another meter, so in other words we have meters squared on the top, and then in our denominator we had another meter squared. So those meters squared canceled with that meter, and all of our units are gone now except for the ohm. So it is 0.17 ohms is the resistance of that wire. Okay, that's important to know because that will tell you how much current can go through that wire. And if you want to limit the current on something, you probably want a wire that has more resistance. If you want to allow more current to come through, you want a less resistance, a bigger wire, which is going to have less resistance. Now, you might think, well, wouldn't you always want a lot of current? No. If you have too much current, you can blow things out. Like you can actually start fires if there's too much current in there. So you want to have some resistance to limit that current so that not too much is coming out. Again, kind of like the fire hydrant analogy. You don't want too much coming out. Too much sometimes is a bad thing. Okay, the next concept to talk about is Ohm's law. Ohm's law is stated in terms of V equals IR. On the AP sheet, it is actually stated a little bit differently. The only difference is, I'm going to come down here, the difference is on the AP sheet, it gives it as I equals change in volts over resistance. Where I is the current, V is the voltage. Voltage is also called potential difference. Those two phrases mean the same thing. And some people who are not familiar with DC circuits, electricity, might not understand what those mean. We're going to hope to come to figure out what all those mean. So V is voltage, I is current, R is resistance, and we put them together like this. This is, again, kind of like F equals MA. This is like the one that you memorize. So V equals IR is the one that you memorize. Just for me, it's easier to memorize it that way. But yet this one, the I equals change in V over R, that one sometimes is more helpful because it actually shows you how much current you have. Typically, that's what you're wanting to find. How much current is there going to be? Well, how much voltage is in the battery and what kind of resistance do you have in your wire? That's going to tell you how much current you have. So this is a little bit more practical, whereas I just personally memorize V equals IR. Okay, so different objects resist the flow of current more or less. It's electrical friction. That's what is going on. And so a toaster element, if you have a toaster at home, when you turn on that toaster, it gets real hot, right? That's because there is a lot of resistance creating a lot of friction, creating a lot of heat. Same thing with your, if you have, it says electric range. That's like your stove. If you have an electric stove, some people have a gas stove. But if you have an electric stove, same thing. You turn it on, it gets red, it gets hot. And a light bulb, an old-fashioned light bulb, is the same thing. It gets hot, and therefore it puts out light. The less resistance there is, the faster the current will flow. Back to the hose. You know, if you have a really skinny hose, you're going to have not much flow. If you have a really wide, big, fat hose, you're going to have a lot of flow. Same thing with wires. A skinny wire, a little bit of current. A big, fat wire, a lot of current. The more electrons that you want to flow, that's called the potential difference. That's voltage. Then you have a faster current. So if you have a bigger battery, you're going to have more current. Okay, let's look at some problems that are basically just figuring out how to plug stuff into our equations. So, what current will be produced when a 150 ohm resistor is connected to a 12 volt battery? Okay, I is current. So I'm going to use this bottom one because it's already set up for I. And so I'm going to take my 12 volts, divide by my 150 ohms, and I'm going to divide that on my calculator. Take a second to take out your calculator. That answer is given to us in amps. And amps is just a capital A, so we would just say 0.08 A. That's 0.08 amps. That's how much current. Amps is measuring current. That's how much current you will have if you have a 150 ohm resistor and you have a 12 volt battery. And we're going to do some lab work with light bulbs, and I like light bulbs because they allow you to see how much current is going on, because it'll get brighter or dimmer in different situations. So we'll be able to see this played out with some both online labs and real labs in the classroom. Okay, next question is very similar. What is the resistance to a circuit? But this time they're asking, okay, what's the resistance? We know the output, it has 0.04 amps, and we know the input, it has 12 volts of battery, but there's some kind of resistance going on. What is that resistance? We could use either equation. I might for this one, you could move it around. You could take this top equation and you could divide by I. So you get V over I equals R because we're solving for resistance. And so we can just use that setup. And so we have a 12 volt battery. We have 0.04 amps. I'm going to divide that on my calculator and see how much resistance there is. And so 12 divided by 0.04 is 300. It's 300 ohms. That's how much resistance is in that circuit. Either the wires themselves have that much resistance, or I've put in some things called resistors, which are put there on purpose to slow things down. Okay, a little bit of things to talk about. One thing is batteries maintain a nearly constant potential difference. It's the current that varies. And so when I say potential difference, again, I'm talking about voltage, which voltage is a phrase that at least some of us have a little bit of understanding of, but potential difference actually tells us what's going on. And so anyway, both of those are just talking about that batteries maintain a nearly constant potential difference or voltage. It's the current that varies. Okay, another thing, remember we talked about this a second ago, resistance is a property of a material or a device. So it might be made out of copper, it might be made out of silver, it might be made out of steel, it might be really long, it might be really short, it might be really wide, whatever. All of that adds up to resistance. Another thing, current is not a vector, but it does have a direction. And so when we're talking about circuits, do you know that the word circuit just means circle? Okay, so if I make a circuit, I'm making a circle. You will have a battery set up and there will be electrons flowing. And those electrons are flowing all the way around and they create a circuit. Current is not a vector, but it does have a direction. It's going to tell us which direction are those electrons flowing. And so just keep in mind current does have a direction, very much like water. If you think about like at the Matt Ross, you've got the little lazy river, okay? It has a direction to it. Also, current and charge do not get used up. Whatever charge goes in one end of a circuit comes out the other end. So if this is a battery and it's giving out charge, it doesn't just lose the charge, it actually then comes back in and it keeps going around and around and around. So current and charge don't get used up. Whatever charge goes in one end of a circuit comes out the other end. Now, I realize batteries do get used up after a long time. That's a little bit different than what's going on in a circuit. I mean, it's just kind of a fact of life. You're going to lose some electrons along the way. Okay, it's not a perfect circuit. You're going to lose some. But the main thing here is that they don't get used up. It goes in one end, it comes out the other end. It goes in one and comes out the other end. Okay, let's turn the page.